I want to give you kind of an overview of Lesson 12, which is the topic is quadratic functions, polynomial functions, and rational functions. And I want to focus first on primarily the idea of polynomial and quadratic functions. And if we're going to talk about it, we need to first define what is a polynomial function. Well, a polynomial function kind of the definition looks very daunting when you look at it, but hang on and I'll see if I can make it a little bit simple for you. But the formal definition of a polynomial function says, let n be a non-negative integer and let a sub n minus 1, a sub 2, a sub 1, a sub 0 be real numbers with a sub n not equal to 0. Then the function f of x equals a sub n, x to the nth, plus a sub 1, x to the n minus 1, a sub 2, x squared, plus a sub 1, x, plus a sub 0 is a polynomial function of x with a degree of n. One of the things I want you to notice in this kind of crazy definition is how the subscript on the a and the exponent on the x match. Okay, so you would have a sub 2 with the x squared, a sub 1 with x to the understood 1 exponent. Okay, and so really, honestly, you've already been learning about polynomial functions. You just didn't realize it, or we didn't call it a polynomial function. Here are some examples of a polynomial function. F of x equals 5 is actually a constant function which would have a degree of 0. And in terms of that crazy notation, this would be like having f of x equals a sub 0. Then you have linear functions, which we've talked about previously. This is like having f of x equals a sub 1 x plus a sub 0. Now, you're used to seeing a linear function usually in the terms of like mx plus b, where m is the slope and b is the y-intercept. So really what's happening here is they're just slightly changing the notation, because with a polynomial function, you could feasibly have, 26, 27, 28, even 30 values, 35 values. And so if we just use like A, B, C, D, E, we run out of letters if we have more than 26 values. And so they begin using this subscripted system. So don't get so caught up in that. It's just the notation that they use. Then the third example there, you have f of x equals x squared minus 3x minus 4. And again, this would have that notation. You would have a sub 2 x squared, in this case, minus a sub 1 x minus a sub 0. Now, the standard guidelines typically have it as pluses. And so what we're looking at are problems where you have exponents or powers on the x's, things like x squared, x to the 4th, x to the 5th in a problem. The x squared is what we typically call a quadratic function. And you may already be familiar with quadratics, and typically quadratics, we usually write them as ax squared plus bx plus c. And again, they're just slightly changing the notation to allow for the fact that you could have more than 26 values and we'd run out of letters of the alphabet. As you get into those with higher powers like x to the 4th or x to the 5th, the graphs themselves become a little bit more involved, and so we have to have some additional techniques for finding the zeros, finding the y-intercept, and that sort of thing. Some of the characteristics that are common to all polynomial functions of degree n is that they are functions, which means they will pass the vertical line test. The domain or the input for a polynomial function is negative infinity to positive infinity or all real numbers. Now, the range is going to vary depending on the type function you have, whether it's x squared or x to the fourth or x to the fifth. A polynomial function could be solely increasing, just decreasing, or both. So you're going to have those relative minimums and relative maximums. You can also have absolute minimums and absolute maximums. The function itself could be even or odd, meaning it could be symmetric to the y-axis or symmetric to the origin. You could have zeros where you cross the x-axis. Not many, but some polynomial functions do have an inverse because they'll pass the horizontal line test. Polynomial functions are continuous, meaning that you can draw the entire picture without lifting your pencil off the paper. It is a curve, so you have smooth, rounded turns and no sharp points. And one of the key things to remember, or one of the important things about polynomial functions, is that they're grouped or classified by the highest degree, and the highest degree corresponds to the highest exponent. So we group them according to their degree. The degree corresponds to the highest exponent, and that's going to be important. Now, throughout Chapter 5 or Lesson 12, you're going to be looking at, in Section 5.1, we look at polynomials with a degree of 2, which are typically called quadratic functions. And then in sections 5.2, 5.3, and 5.5, we look at polynomial functions of x with a degree of 3 or more. And we're going to take a look at those specific polynomial functions with a degree of 3 or more in a separate video.